F is 18. Then we are told it produces produces an image. It produces an image, which is okay. It produces an image which is 6 centimeters away from the mirror. So V is 6 centimeters. And you see, this is a convex mirror. A convex mirror would, at every object position, produce a virtual image. Okay, 6 centimeters away. Calculate the position of the objects using RP and NC. So we are to calculate for the position of the objects using both conventions. So using RP, please, whenever you are solving this, state which of the conventions you are using. So using RP convention, anything real is positive. Okay, you know, and a convex mirror has a virtual principal focus. So if under this convention, F will be minus 18. A convex mirror always forms a virtual image. So B would also be minus 6. So 1 on F is equal to 1 on U plus 1 on V. When you are solving this, I advise that you substitute your values before. You don't make 1 over U the subject, because when people make 1 over U the subject, yes, they tend to forget that the V is negative. But if you can see that, that's also fine. So in that case, or in this case, we have minus 1 over 18 minus V is also minus 1 over 6. But some students usually forget this. They will just bring this minus and that's it. So we have 1 over 6, which is positive, minus 1 over 18. LCM 18, 6 goes into 18, 3, so 3 minus 1, giving us 2 on 18. And 2 on 18 is 1 over 9. Therefore, U is equal to 9 centimeters. And since the object is real, we must have object distance, which is positive. Then using NC, okay, for NC, F will be positive 18, because it is at the other side, back of the mirror. So it follows, the object distance follows the direction of the incident ray. Then V would also be positive. V will also be positive because image is virtual. So that is 6 centimeters. Therefore, 1 over U will be equal to 1 over F minus 1 over V. So that when we put our values in, we have 1 on 18 minus 1 on 6. LCM 18, 1 minus 3. All right. Michelle, noted. I'll send you information. in the course of your dropping out of the session. So minus 2 on 18. And this is also minus 1 on 9. Therefore, you will be equal to negative 9 centimeters. And you must be negative because the object is in front of the mirror. So object distance will be against the direction of the incident light. Okay. So these are what must go into the problem. Then I also gave one particular, I forwarded another question, but this one I deliberately gave it out to those who had submitted the first one. This particular question. I sent it out to those who had completed this first one. Let me read the message from Angie. I'll send videos. Okay, I'll send videos. So let's quickly look at this. I've just posted that question on the page. A convergent mirror has a focal length of 30 centimeters. Abinema, please mute yourself. So this time around, it's a convergent mirror. Convergent or concave. And we are told it has a focal length of 30. So F is equal to 30 centimeters. Rays from a 2.0 centimeter high filament bulb that pass through the mirror form a virtual image. So we are given the object height, HI 2.0 centimeter, forms a virtual image at a distance of 50 from the mirror. So V is 50 centimeter. A, where is the filament bulb located? So A, we are looking for the object distance. And B, what is the height of the image? Image height. Okay. Now, before you even solve this question, there are stuffs you must apply from ray diagrams. And what is that? You know that there is only one instant where a convergent mirror will form a virtual image. And that is when the object is between the pole of the mirror and the focal point. Okay? When the object is between the pole and the focal point. So it means that for this image to be formed, the image object distance U must be less than the focal length F of the mirror. And this is what must guide your calculation. If you are getting any value of U, which is greater than F, or which is even equal to F, note that a virtual image will not be formed. And so some of you, upon solving, had U value to be 70, and I was laughing at you. I was laughing at you, meaning that you were not applying the theory. You were not applying the theory. Are you there? Class, are you there?
Yes, please.
So, an indication that you were not applying the theory, if you solve this and get a value which is even equal to 30 or greater than 30. Let me quickly drop attendance, okay, before we look at. So please, going forward, whenever you are solving this, do not forget to pick clue from the ray diagram. That will help a lot. Okay, so if I'm to find or determine where the filament is located, then that's the object distance. So using RP, quote the mirror formula, and RP, converging mirror has a real principal focus. And so F will be positive. So 1 on 30 is equal to 1 over U. U is what we are looking for. Now we are told the object is virtual. So V will be negative. So minus 1 over 50. Make 1 over U the subject. And you have 1 on 30 plus 1 on 50. Determine the LCM. LCM is 150. Okay. 3 goes into 150. Yeah, 30 goes into 150. 5 times 1. And then 50 goes into 150. 3. 3 times 1. So we have 1 over U to be equal to 8 on 150. Therefore, U is equal to 150 over 8, which is 18.75 centimeters. Okay. So that, and compare what you have with F. F is 30. So clearly, since U is less than F, we are expected to have a virtual image. Okay. Then the second question asks that we find what is the height of the image. Linear magnification, please, when you are writing this, put that into the magnitude value or absolute value symbol. Then it's a small letter M, not capital letter. Capital letter M has 8 different applications. So small letter M, this is equal to transverse magnification. This is lateral, and it's also equal to transverse magnification HI on HO. Okay, so V is 50. And by this symbol, we are looking at the absolute value, numerical value. Forget about minus 50, because we are looking at the absolute value. So 50 over 18.75 is equal to HI, which we are looking for, divided by 2. Therefore, HI is 50 over 18.75 times 2. And this must give us about 5.33 centimeters. Okay. So this is what I was expecting you to actually submit. Is there any question? If you have any question, quickly ask. Isabella.
Sir.
Hello.
Represent on again.
Isabella, where?
The U is equal to 150 over 8.
Okay, so we are looking for the image height. The image height, or the height of the image. We've done lateral magnification, and lateral magnification is equal to image distance V over object distance. Then we also saw transverse magnification to be equal to image height over object height. Geometry, or which is theory, and then experiment has proven that lateral magnification is equal to transverse magnification. So it means that V over U is equal to HI on HO. This is what we are calling as the magnitude of the linear magnification of the mirror. Okay, so magnitude of M is equal to V over U, which is equal to HI on HO. And last time we also learned that when magnitude of linear magnification is equal to 1, it means that image distance is equal to the object distance, or image size is equal to object size. And this is what we saw under mirrors, in a plane mirror. In plane mirror, object height, object distance is always equal to image distance or image height. Now, if this is greater than 1, image is said to be enlarged. Image is enlarged. And if linear magnification is less than 1, image is diminished. Now, look at what we had. 50 divided by 18.75. Isabella, what is 50 divided by 18.75? Anybody? 50 divided by 18.75. Saki.
2.67.
Come again.
2.67.
2.67. So this value is greater than 1, implying that the image is magnified. Saki.
So please, when we're proving the mirror formula, you also used something related to height, which was object height over image height.
I remember we took the inverse. You see, in one of the equations, it was HI over HO. And in the other equation, HO So we took the inverse to have them both equation as the same. That's how come he equated it.
I'm saying, why is it that the formula relating to height, what we used to prove the mirror formula, why is it that we didn't use it to solve this question?
Oh, we can also use it, provided when we equate, we have all the information to use. And it must give us the same results. Saki, are you okay?
Yes, sir.
We can also use that as well. All right. Today, let's look at refraction of light. So we've done reflection both in plane and spherical mirrors, and we've done the mirror formula, refraction of light. One of the other properties of light. Light can be refracted. Class, what is refraction of light? Frank. Frank, go ahead.
Refraction of light is the bending of light as it passes from one medium to another.
So the bending of light as it passes from one medium to another medium. Thank you. So this time around, this is about bending of light. Okay, so refraction can be explained in several ways. One of it is the bending of light from one medium to another. Yes, can we also explain refraction of light differently apart from bending? Apart from bending, can we also define refraction of light in a different? Yes, Ablina Afo. Okay, because of time. So we can also define refraction as a change in the speed, of light as it moves from one medium to another. Change in the speed of light from one medium to another. This bending thing can also be defined as change in direction. Okay, bending of light from one medium to another, or change in direction. Direction of light from one medium to another. Then the third definition can also be change in the wavelength. Change in the wavelength of light from one medium to another. Okay, so it means that when light moves from one medium to another on a certain condition, its direction can change, that is bending. Its speed can change, and its wavelength can also change. Now, class, what actually causes refraction of light? What actually causes refraction of light? Anybody? Francis?
So can we say the optical density of the how do I say the substance that is passing through?
Yes. Oh, we say use material instead of substance. Okay, substance will also do, but material will be fine.
Okay.
Now, whenever light passes through one medium to another, I'm coming. Whenever light travels from one medium to another, and the two media have the same density, light will never bend. So when you on a torchlight, so long as the torchlight continues to move through air, it will never bend. However, when it encounters another medium whose density is different from the first one or from air, then it will bend. Okay, so refraction occurs due to difference in density. Okay, refraction occurs refraction of light occurs due to the difference in the densities of the two media, meaning that if the two materials have the same density, it will never bend. Okay, it will never bend. Now, in defining this, we use the word or the adjective optical. Optical, because for us to have an evidence of refraction taking place, the two material must be such that they will freely allow light to pass through. So yes, their densities must be different, but the materials must be such that the two densities must be such that they allow light to. So if they have different optical density, all right. So when light travels through air and it hits glass, a transparent glass or prism, then you can see the bending of light. When it passes through a lens, okay, lens will readily allow light. But the moment light hits a mirror, because for mirror, one of the side is coated, you cannot see whether refraction has occurred or not. So the material must be such that it readily allows light pass through and must have a difference in its density. That's why we use difference in their optical densities. So the key factor which affects or determines refraction is density. All right, let's look at applications of the concept of refraction. applications of refraction. Yes, can you share with me practical applications of refraction of light around us? Everyday occurrences which explains the concept of refraction. Anita, give me one. Okay, Saki will break the ice for us. Saki.
Yes, when it's raining, the formation of a rainbow.
Formation of rainbow is dual something.
Why now?
It's both reflection and refraction. So it
Okay,
isn't exclusively refraction.
sir,
Okay.
please, what about the lens?
And the lens refracts. The lens refracts. Okay, others want to also contribute. So, Francis.
Sir, the prism, like using a prism to find the different spectrums of light.
You see, I want us to discuss natural occurrences which explains the concept of refraction before we talk about the Fabian-made refraction. Okay.
Okay.
Angie.
So why a pool looks shallow than it actually is?
Thank you. So in sunny, another hand is up. Let me. Genius, Saki, are you the one?
This is okay.
All right. So in sunny afternoons, when you happen to visit a pool or water bodies, which are not so deep, when you look at the bottom of the pool, it always appears closer to you. Okay, or the pool always appears shallow. That apparent shallow depth of the pool or streams is as a result of refraction. And in fact, I have a practical experience with this. I remember when I was younger, I tried swimming in a pool during a sunny afternoon. So when I stood beside the edge of the pool, then I dived into it thinking that, oh, the depth is just here. Only for me to be deceived. I fell heavily within the pool. When I was there, I thought, oh, this one is just here. So, but I fell. Then I don't know what I saw actually deceived me. I wasn't a disciple of physics then. And so I did not understand why okay. So the apparent shallowness of the depth of a pool. So apparent shallow depth of a pool during sunny afternoons. Then up here, let's share. So this is 1, 2. Frank.
A straw in a glass of water appears to be bent.
A straw, pencil, pen, spoon appears bent. Okay. Spoon, pencil, etc. appears bent at the interface between air and air and water, or the boundary. Good. Saki.
And please, can you say when you use a magnifying glass to view some objects, can you say it's an application of refraction?
Exactly. It is. So when you place a coin or your hand behind a mirror, a lens or prism, your hand or the coin appears magnified. Okay, that is also an application of refraction of light. Yes, more views. Then mirage formation. Formation of. I'm coming. Yes, Elikem.
Sir, please, creating rainbow effects. Creating rainbow effect.
Natural rainbow is due to both reflection and refraction. But you creating rainbow effect using what?
A glass prism.
Yes. So when you are saying this, you must explain. Okay. Yes, Bashira.
Please, the twinkling of stars in the night.
Yes. Twinkle, twinkle, little stars. Okay. That is due to of stars in the night. Okay, in the sky. And then I said mirage formation. Mirage formation. What is a mirage? A mirage is that apparent pool of water on the surface of roads during sunny afternoons. That is a mirage. Okay, the apparent pool of water on the surface of roads during sunny afternoon is a mirage. This is also due to refraction of light. Then, whenever you visit the stream or the pool and you see fishes swimming in the pool or the stream, the fish always appears closer to you. Growing up, whenever we make that visit and then we dip our hands down to catch a fish, we are always swept, or the fish always swerves us due to the fact that the apparent position of the fish is actually not real. It's a virtual position. So you dip your hand into the water and the fish also swerves you. These are all natural applications of mirage. Frank,
Sir, please, I have a question.
go ahead.
When like there's heat or fire, when you look around it, it looks like wavy. Is
When
that
you look at what?
fire, like above it or beside fire, like close to it? It looks wavy.
Radiant wave.
Yes, please.
Yes. Have I answered it?
Is it an application of refraction?
No, that is reflection. The heat from the sun incident on the stones or objects and it reflects. Refraction to occur, the wave must actually pass through the material. But when it bounces back, it's reflection. That is why in reflection, if the material is not the type which will allow light to pass through, you will not see it happening. Are you okay?
Yes, please.
All right. All right. So these are practical or natural occurrences which explain the concept of refraction. We can also talk about a lot. So you can add on. All right. Now, before we let's look at the laws of refraction. Laws of refraction. So if you have two different media, let's assume this first medium is air and the second medium is glass. So in this case, light is traveling from a less dense medium to a more dense medium. Let's draw a normal to the interface. So this is normal N. An incident ray. So this angle between the normal and the incident ray is the angle of incidence. Now note that whenever light incidents on a medium, in fact, part of the incident light is reflected and part is refracted. So there will be small parts of the incident light which will be reflected. So we have a weaker reflection and a stronger refraction if the material, the denser material is such that it allows light to pass through it. So that is what happens whenever light incidents on a transparent material. Part of it will be reflected, but it will be weaker. So this is a weaker reflected ray. If the material is a transparent one, a transparent material, then we'll have a greater part of it being refracted. How will it bend if the light is from less dense medium to a more dense medium? The refracted ray is bent towards the normal. So we call this as the refracted ray. So whenever light travels from less dense medium to a more dense medium, the refracted ray is bent towards the normal. Okay, so we call this angle as the angle of refraction, R prime. We'll call this as angle of reflection. So where I is equal to the angle of incidence then R is the angle of refraction sorry, this is the angle of reflection, and R prime is the angle of refraction. Alvin.
Sir, please, is it always going to bend to the medium, to the normal?
It will bend towards the normal if the light is from less dense medium to a more dense medium. So here we are looking at when the light is from air to glass. Glass is denser than air. If it also travels from water to air to water, it will also bend towards the normal. So this is exclusively for when the light is from less dense medium to a more dense medium. Are you okay?
Yes.
Now let's look at the other way around as you just asked. Jasmine, are you there? Anna?
Yes, sir.
Anna, are you there? So this is the boundary or the interface separating the two media. Okay. So indicate that as a boundary. Boundary. Or the interface separating the two media. Point of incidence. So let's draw a normal. So if this is the normal, then incident ray small part of it would also be reflected. And this will also, that small part reflected will obey the laws of reflection. That angle of incidence is equal to angle of reflection. So over here too, that law is obeyed. So this is R, which is also equal to I. But this is very weak reflected ray. Now, because this time around, let's assume the ray is from the opposite, glass to air. So from more dense to a less dense medium. Okay. Don't forget that for refraction to occur, the two media must just have different densities. So this time, the refracted ray will bend away from the normal. Will bend away from the So this whole angle here is the angle of refraction. Is the angle of refraction. So what you must actually note is that whenever light travels from a less dense medium to a more dense medium, light, the part of the refracted ray or light is bent towards the normal. Light is bent towards the normal. So this is refracted ray bending towards the normal and here refracted ray bending away from the normal. So weaker reflected ray and then stronger refracted ray. All right. So let's quickly look at the laws of refraction. Laws of refraction. Can somebody help? What is the first law of refraction? What is the first law of refraction? Anybody? Anita. Anita, let me hear from you. Anita.
Yes, sir.
Help me with the first law of refraction. Okay.
A ray from a less dense medium will bend towards the normal in a more denser medium.
Okay. Not bad. Frank?
The refracted ray passing through a less dense medium bends towards the normal.
Okay. All right, not so direct as this one though. But then, if you have Angie, your hand was raised.
This was a mistake.
Okay, so the first law is similar to the first law of refraction, just similar to the law of reflection. And that is the incident ray the normal at the point of incidence and the refracted ray all lie in the same plane. In the same plane. So it's just similar to the first law of reflection. The incident ray, the normal at the point of incidence, and the refracted ray all lie in the same plane. That's the first law of refraction. Then the second law of refraction is termed as Snell's law. Snell's law, named after one physicist, Willibrod Snell. Willibrod Snell. And Snell's law, which is the second law of refraction, says that for any pair of media of media of different refractive indices for any pair of media of different densities or optical densities, the ratio of the sign, S-I-N-E, sine, the ratio of the sine of the angle of incidence to the sine of the angle of refraction S equal to a constant. This is Snell's law. So Snell's law says that for any two pair of media of different optical densities, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant. Okay, all that Snell is saying here is that if you have any two media of different densities, so if supposing this is the incident ray is from air to water. So if the light is moving from air to water, how will it bend? Will it bend towards the normal or away from the normal?
Say please towards.
Away from the normal.
Towards the normal. So clearly, it means that the angle of incidence will be greater than the angle of refraction. So this is I. And since this is the refracted ray, this will be R. What will also be the relationship between the angle of incidence and the angle of reflection? What will be the relationship between the angle of incidence and the angle of reflection? Yes, Aki.
Angle of incidence will be the same as the angle of reflection.
Okay, Martin. What do you also say, Martin?
Sir, please, it would be the same as the angle of incidence, the angle of refraction.
But what will be the difference? The difference is just that the reflected ray will be weaker in intensity because the greater chunk of the light will be refracted. So do not forget this. So weaker reflected, but this will also be I. So all that Snell is saying is that for any two pair of media, whenever you take the ratio of the sine of the angle, sine, cos, and tan applies to angle. So if you take the ratio of the sine of the angle of incidence to the sine of the angle of refraction, it must be equal to a constant. So long as the two media have different densities, just as the Snell's law. Are you okay? All right.
So please can you go over?
Snell's law.
Yes, please.
So Snell's law is saying that for any two media of different optical densities, whenever you take the sine, the ratio of the sine of the angle of incidence to the sine of the angle of refraction, it must be equal to a constant. Okay, so this is Snell's law in mathematical form. Sine I over sine R must be equal to a constant. What it therefore means is that so long as the two media are not varied, but it's about the same media, whenever you vary the angle of incidence, 30/degree, 40, 50, all this will give you a certain value of R, okay? But so long as it's about the two media, let's assume that R value for an angle of incidence of 30s. 23. This is 21. 19. I'm just assuming values. All that Snell is saying is that whenever we take the ratio of sine I to sine R, if this ratio is given us maybe 1.2, this ratio must also give us a value close to 1.2. Or the same value, almost the same value or values which is close to 1.2. That is what we mean by the ratio being constant. We'll go deeper, so you don't worry. So this is Snell's law. So we have two main laws of refraction: the incident ray, the normal at the point of incidence, and the refracted ray all lie in the same plane. And then the Snell's law, which also says that the ratio of for any two given pair of media of different optical densities, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant. Okay. Now, this constant value, the constant is what is known as the refractive index. Refractive index of the material. So, you see, look at these examples we considered. Assuming if, as we took the ratio of sine and R, we got a constant value of around 1.2. This constant value is the 1.2. Constant means it's an unchanging value, the same. This 1.2 is the refractive index of the denser material here, which in this case is water. All right, please, a minute. I'm coming. I'm picking it. Okay, so this 1.2 value is what we term as the refractive index of, let me qualify, we'll come to it, the absolute refractive index of the denser material. Absolute refractive index. Yes, Gideon.
So is it because the smallest value, that's why it's the absolute value of the
Is it because it's
the smallest value among the two values over there?
No. I'm just assuming values. Okay, we'll come to it. Where I will explain further. Okay. So whenever light is traveling from a less dense medium to a more dense medium, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant. This constant value is termed as the absolute refractive index of the denser material, or medium. Okay, so in this case, the denser material here is the water, and because light is moving from air to water, so we assume that this 1.2 value is the refractive index of water, but that's not the actual value. Refractive index of water is 1.33. Now, what we mean by refractive index of a material? What do we mean by the refractive index of material? The refractive index of a material is the measure of the material's ability to bend light. The refractive index of a material is the measure of the material's ability to bend or deviate light. Okay. So glass, for instance, has an has a refractive index of 1.5. So example, can I move to the next page? No.
Yes.
Okay. So example, Edmond, you are still writing.
Yeah, sir, please, the previous page, I couldn't see the last word. To bend or
to bend or deviate.
Deviate light. All right, thank you, sir.
To bend or deviate. So the absolute refractive index of glass, or the refractive index of glass is 1.5. What it simply means is that glass can bend light 1.5 times as can be done by air. If the refractive index of glass is 1.5, what it simply means is that glass can bend light 1.5 times as can be done by air. Or don't forget, 1.5 is also equal to 150%. So it means that glass can bend light 150% times as can be done by air. Okay. 2, the refractive index of water. Refractive index of water is 1.33, meaning water can bend light 1.33 times as can be done by water, or 133%. Okay, and this is what we mean by absolute refractive index of. So Snell's law, that constant value is the refractive index of the or the absolute refractive index of the denser material. Angie?
So does that mean that the refractive index is always like a comparison to A?
Exactly. To something else. But when we'll go deeper, you don't worry. So refractive index, we have absolute refractive index, we have reverse refractive index, and we have relative refractive index. They are all comparative analysis to other materials. Okay.
Okay, sir. Thank you.
All right. So that is it with refraction. So it can be change in the direction, change in the speed of light, change in the wavelength of light from one medium to another. Meaning, whenever light travels from one medium to another and their densities are different, the direction of the light can change. The speed of the light can also change, and the wavelength of the light can also change. However, the frequency of the light can never change no matter the difference in densities of the material. So note that as well. Whenever light travels through a material or a medium, its direction can change, its speed can change, its wavelength can also change, but the frequency of the light will never change no matter the difference in the optical densities of the materials. So frequency is always constant, but direction, speed, and wavelength can always change. So by this diagram, what do you think will be the nature of the medium involved? By this diagram, what do you think will be the nature of the medium involved? Medium one. What will you give us medium one? And what will you also give as medium two by this diagram? Yes, can anybody help?
Air and glass.
Air and glass, meaning in terms of density, how would you compare the densities of the two? Ella?
The medium 2, which is the glass, has higher density as compared to medium 1, which is
Thank you. So basically, medium 2 must be denser than medium 1. Now, just as we also saw for reflection, this incident ray ideally has this part. Ideally, this is the supposed part of the incident ray. But due to difference in densities, it couldn't go this distance straight. And it is now forced to be here. So we want to determine this angle. We know this angle is the angle of refraction. But what will be this angle X? Yes, can somebody help? How do we determine the angle X? Anybody? Angie?
So please, I think it will be X equal to I minus R.
Why? Why do you think X?
Because I feel like the angle of incidence is equal to the sum of R and X.
By what mathematical reason? By what mathematical reason? Martin.
I won't say
okay,
the
say
angle.
join voices
Alternate
and answer. Okay, is it alternate? No.
Vertically opposite.
Vertically
Yes, vertically.
opposite angle. Thank you. So I by vertically opposite angle reason must be R plus X. X is equal to I minus R. This angle X is known as the angle of deviation. So where X is known as the angle of deviation. Okay, so I am representing the angle of deviation by this symbol sigma. Sigma is equal to I minus R, where sigma is equal to angle of deviation. I is the angle of incidence and R is equal to the angle of refraction. Class, what letter do you think would represent the angle of reflection? What letter will represent the angle of reflection? Anybody? Saki? Ella? Eh? I. Yasmin, you also talk. So that's it. So note this technicalities. I'll be sending you beautiful questions where you engage your brain so much. And don't forget that, Zaki, your hand is still up. What is your secret?
Sir, please, it was a mistake.
Okay. So this is how to Gideon.
So the new line I'm drawing will be the angle of reflection. So can I also say that one will be R?
That will be I. That's what they just answered. But angle of incidence equal angle of reflection. Here, the only difference is that the reflected ray will be weaker, whereas the refracted ray is brighter because the second medium is a transparent medium. So once the medium is transparent, a greater part of the incident light will be refracted, whereas just a small part will be reflected, but still would obey the laws of reflection. Okay, so this is what goes into refraction of light. We'll go into it into details. Okay, tomorrow physics Alt A practical S will be ongoing. I'm only hoping that by 3:30 students must be done. If we are not able to finish within 3:30, then I'll push the class during the evening. Okay.
Okay, sir.
All right. So this is where we end today's show. We'll continue this tomorrow. Okay. So please do the revision for me. Yes. Just be revised. And please, I forwarded Fantipim's assignment. Okay, use it. Begin answering it, just to be able to apply whatever you've learned in solving problems. All right. Thank you so much, and bye-bye. Your video, as usual, will be sent. Bye-bye.
Bye.
Bye.
Okay. Yeah.